Yeah, good afternoon, everyone. Today is another day. We are going to continue from our last class where we stopped. You know, I'm now bringing a board here now. I told you before you start your calculation, you prepare calculation sheets. This is a member reference. These calculations, these outputs. All right. From our last class, sorry, in our last class, we were able to get our UDL ultimate design load to be 14.52 kilonewton per meter run. All right. Now we have our D was 124 millimeters. Right. So what we need to do now is to get our bending moment coefficient. And again, from our design, have that Ly over Lx, that's the ratio now, how to get the bending moment coefficient. Ly over Lx. Now design, we have that Ly is equal to 4425, then Lx 4112.5. If you compute this with your calculator, you're going to have approximately 1.1. Now you move with this one, you can go to the table, bending moment coefficient table, where all the cases are listed there. In this particular panel, it's two adjacent edges is continuous. So if you go to that particular table, you can refer it to, you can write here BS 8, you can write here BS 8110 1997 table 3.14. Table 3.14 will take you, we'll go to that table, then we'll obtain our bending moment coefficient, have moment coefficient. All right. Now for short span, the negative moment coefficient will be from this table. We're able to get the ratio to be 1.1. You go to the table where we have 1.1, you trace it down to two adjacent edges discontinuous. All right. Now, two adjacent edges discontinuous, the bending moment coefficient for the ratio of 1.0, trace it down, is negative 0.056, while the positive is equals to 0.042. All right. Then the long span. All right. The negative moment coefficient is equals to, we also go to that place, trace it down. But in this case, we have a long span coefficient for all values, in that particular case. This is case 4. So you go to the long span, the negative value is 0.045, while the positive value goes to 0.034. All right. Now, when you are now designing for the short span, you use this positive value for the mid-span coefficients. For the mid-span, when you are designing for the span, then you use negative value for the continuous edge. All right. Likewise, when you are designing for the long span. Okay. The next thing to do now is to, getting the value of our bending moment, which is M. M is equals to, we are making use of, let's call this one mid-span moment. Mid-span moment. All right? The M is equals to 0.042 multiplied by our UDL, 10.52 multiplied by what? Our LX, that is 4.1125 square. Converting to, this one is in millimeters, so we're converting to meters now. All right, so our value for M will now be equal to 0.042 multiplied by 14.52 multiplied by 4.1125 squared. We now have 10.314. This is kilonewton meters. We can still convert this one to Newton millimeter, which will be equal to 10.314 times 10 raised to power 6 Newton millimeters. Alright, kilonewton, 1000 Newton make 1 kilonewton, 1000 millimeter make 1 meter. So that is why this one is 10 to the power 6. 10 times 10, 1000 times 1000, that's 1 million. Alright, okay, we have been able to obtain the value for our moments, which is this. We'll now move straight to our K. Alright, let me clean this. Quickly move to our K. Our moment equals to 10.314 times 10 raised to the power 6 Newton millimeter. Then K is equals to M over FCU BD square, where FCU characteristic strength of concrete to be 20 Newton per millimeter square. Then B is taken as 1000 millimeters. Then D is equal to 124 millimeters. All right. Now we'll go straight to computing the value of K, which is 10.314 times 10 raised to the power 6 all over 20 multiplied by 1000 multiplied by 124 squared. All right, this one will give us, you compute that, 10.314 exponential 6 divided by 20 multiplied by 1000 multiplied by 124 squared. This one will give me 0.034 as our K. The next step is to getting our lever arm. Lever arm is, this one is less than 0.156. This is okay. Then our next step is lever arm. This is from this formula, 0.5 plus square root of 0.25 minus K over 0.9. That's how to get the value for our AL. All right. Now we've gotten the value of K, which is 0.034. So we'll now move straight. This is now 0.5 plus this 0.25 minus 0.034 over 0.9. This must be less than or equal to 0.95. If it is, by the time it computes, this is 0.9. By the time it computes and that this value is greater than 0.95, we adopt 0.95. But if it is lesser, we use the value that's lesser than 0.95. All right. So that's what this one is telling us. So let us compute this. we have 0.25 minus 0.034 divided by 0.9 plus 0.5. So what we have now is LA equals to 0.961. This is greater than 0.95. You use the lesser value, which is 0.95. So LA, we are using 0.95. All right. There is somewhere we are still going to. Okay. Now we'll also calculate for the value of Z. You know that Z is equals to 0.95. That is Z is equals to LED. LE multiplied by our D, which is 24. So we have gotten our LE 0.95, then multiply by D. So let's see, move ahead. It's time consuming. So we now have that Z is equals to 0.95 multiplied by 124. This is equal to 0.95 multiplied by 124. This is equals to 117.8 millimeters. Yes, we have gotten this. So we now move straight to getting the area of the steel. What is the formula for the area of our steel? We have call it like this: AX, all right, goes to M over 0.95 FYZ. All right. Now 0.95 is the factor that is constant. Fy is the characteristic strength of steel. We are saying Fy, we are using characteristic strength of steel to be our 410 Newton per millimeter square. All right. Z is now Z is equals to 117.8. All right. By the time you compute, you now have the 10.314 times 10 raised to the power 6 over 0.95 multiplied by 410 multiplied by 117.8. So if you compute this, we are going to have 10.314 exponential 6 divided by 0.95 times 410 divided by 117.8. This one will give me AS required. This is required now be equals to 224.79 millimeter square. All right, millimeter square. So this is the area. You will now go to the BS code again. Having gotten the value of your area, you now provide provide Y12. Just a moment, please. You now provide your Y12 going to your to be displayed, going to your BS code. You also obtain the value of this. You know, from area required is equals to 224.5. Now, the steel they are producing in this country is substandard. So if I want to provide now, I would have provided Y12 at 300 center to center. That area would have been 377 millimeter square, which is greater than this. It's okay. But the area of steel, the steel in our market today is substandard. So I will now provide Y12, Y12 at, I can provide Y12 at 200 center to center, 200 center to center, as Y12 at 200 center to center will give me 566. Give me AX provided equals to 566 millimeter square. This is greater than this. So what the most important thing now is that the area provided, the area of the steel provided is higher or greater than the area of the steel required after analyzing your structure. So since this one is greater than this, you know, it's very okay. The next step now is to check for your deflection. By the time you use this particular steel and you check for deflection is okay, you adopt this particular steel. So that is that for today's class. Thank you and God bless you. In our next lesson, we'll be checking for deflection. Thank you and God bless you.